we go. Okay. So once again, welcome to and the first day of the energy harvesting 10th and dissemination event. My name is Yuja, and I'm chairing this event. So this is unlike the previous years where we had a one-day whole day dissemination event. This is broken up into chunks of 2 hours across 3 days. So a little bit of background about the energy harvesting network, if you're not aware of. The network was founded about 10 years ago and funded by EPSRC initially for 3 years, chaired at University of Southampton. And later it was supported by KTN. And the network organizes annual dissemination events once a year, or annually once a year, and has been for the last 10 years. So this is the 10th iteration of this dissemination event. And in the past, there have been a few workshops held as well. The Energy Harvesting Network website contains a lot of vibration data repositories, reports, and information related to energy harvesting technology and applications. The network is mainly managed at University of Southampton and supported by Deebing at Exeter and myself at Aston, and advised by the Energy Harvesting Network Steering Board. So the network, so the website on top, please do register if you have not yet registered as a member at the Energy Harvesting Network. The network is comprised of 518 registered companies and institutions across both the academia and industry. And this is the pie chart breakdown of the registered members and the breakdown of the companies and university institutions. So as I mentioned in the previous years, the event has been held in different locations around the UK. So for the photo on the top right, that was from the very first event in 2011 in London. And maybe you can spot yourself somewhere in that photo if you've attended that first event. And the dissemination event, the annual dissemination event, was held in London for the first 6 years. And then on the 7th iteration, it was moved outside London for the first time. It was held in Manchester, as you can see in the second photo there. And then we went around to Bristol and then NPL in London again. And this year it was meant to be held in Birmingham, but as we found ourselves in this rather weird situation that we're in this year, so here we are, the very first online virtual event. But as I say, if G20 can hold their online conference successfully, then so can we. So as I said, the event is in 3 days. And today, the first day, you can download this welcome address PDF, by the way. I put the link in the chat box. So you can download a copy of what I'm presenting here, including the agenda items. The agenda for today is we'll have 4 very exciting talks. The first one from Martin Bragg from Honeywell. The second will be from Alex Weddell from Universitat of Southampton. Then Jonathan Siviter from TEConversion talked to us about thermoelectric energy harvesting. And then Matias from Barcelona will talk to us about the exciting system that he has been developing. And I'll just briefly go through the next 2 days' agenda as well. I'll repeat these when we come to the tomorrow and day after. So tomorrow we'll have 4 other exciting talks, 2 from industry and 2 from academia again, from electricity and Elika from the industry, and Loughborough and Freiburg from the university side. And on the final day, on the final day we'll have, someone raise your hand. Or was there a question? Okay. On the final day, we'll have a talk from 8 Power and a talk from checkout. And then we'll have a panel discussion from 4 panel members and as well as the audience who would like to participate. So if you would like to participate in the panel discussion talking about how the next decade awaits for energy harvesting technologies, then I very much encourage you to come along to the final panel and audience discussion session on Friday. And also, as every slide, you can see that I put in this feedback survey link. So very much hope that you can leave a feedback on the link and give us some opinions on how you would like to see future events and the activities around the energy harvesting network will evolve. All right, as I was talking through, I think more people have joined us, which is a perfect segue into handing over to our first speaker, Martin Bragg from Honeywell, who will talk to us about a practical application with gas pressure regulators. Martin, are you? Martin, are you ready to start your? Yeah, perfect.
Yeah, sorry, I was starting up the slideshow and it wouldn't allow me to unmute my microphone.
Yeah, thank you.
No problem. Let me see if I can enlarge this window. There we go. So, Honeywell Power and Thermal Management. What I thought I'd do here is talk about a little bit of history as to where we've been and what we've been doing to give you a feel for possibly what's happening with applications. And I think it's the applications piece where there's been something of a challenge over the last certainly decade or more. But I'm sharing this particular topic here on the pressure regulator because we actually found a sweet spot where energy harvesting is coming into its own. It's being generated through the situation we find ourselves in 2020 with the global pandemic. And we're finding applications in the order of thousands. In fact, the one customer we're talking to very positively at the moment who is proceeding, they're looking at a rollout of 200 systems to start with, 1,900 across their infrastructure. And overall, if you take the US, for example, there's something like 100,000 of these things. So, nice opportunity to see energy harvesting in our customer base start to take off. I would like to have shared a bit more detail, but we won't waste time here. Just to give you a feel for timelines, 2006, we've been filing patents since 2005 and previously. We've been involved in fabrication, we've been involved in the devices, we've been involved in applications, wireless fluid stream sensors, and we've also had some successes. So if you go back to 2009, we actually won an ID Tech Energy Harvesting Award for the best application, which is our MK electric business. And here you can see the enablement through an ocean, and we had the classic residential switches with the receivers, and we had on the far left the master type product, which is outdoor IP rated. So we've had applications. That's probably been the biggest rollout in terms of quantities, and I see there's a lot more on the market these days, maybe 2 or 3 other players, but not I wouldn't say it's at the point of being prolifically deployed, let's put it that way. We've been involved in rotating shaft vibration, we've been involved in power broking, and the one we're talking about today is the energy harvesting with the pressure regulator, natural gas pressure regulator. And we first filed early 2018. So if you take an overall view as to where we are, what we're doing, where we've been, on the top left is a new business we spun up probably a year or 2 ago now, I lose track, and that's our battery energy storage system. You can see a nice cut through there as to what's going on. That business is growing nicely. You can see in the middle top of the slide what this thing looks like in in the real world, not just a graphic such as the left. On the top right, many years ago, we developed a turbo expander, and the idea of that we'll talk about as we go through the presentation. But we didn't find a lot of uptake in industry, interestingly enough. And it is the year of change in 2020. We're seeing this pick up. I'm going back many years now since we had the turbo expander in the top right. And as I say, we'll talk about it as we go through the presentation. But it was probably a technology that was ahead of what the market was desiring, and that isn't unclassical of all these approaches. And we found that with some of the energy harvesting. On the bottom left, we've been involved in wireless transmitters, energy harvesting transmitters. On the bottom right, we had what we believed and still believe to be one of the better vibration modules out there, power management modules, which was the Perpetuum on the bottom right. Again, we got to the point of launching it. The uptake wasn't particularly strong, but that's just something we've seen with energy harvesting over the years. Why the F-35 fighter in the middle? Well, actually, I'm going to share, by the time I get to the end of this presentation, what we've been doing with our aerospace folks and energy harvesting. And actually, we brought that technology into a Honeywell line of business called measurement and control, process measurement control. We'll talk about that as we go on. So what's the problem statement? Well, we need to understand what the challenge is for the end user to best understand how we supply the solution. And if we look at what was happening, and this is the UK snapshot, I decided Europe-wide or the Americas, keep it focused for now. Your typical distribution company, you can see the names here on the bottom left, they're spending something in the region of $46 million, $40 for American, but $46 million a year typically on emergency repair and maintenance. And if you look at some of the projects that have been gathering funding through the NIAs and the NIC projects, I won't go into what they are, you can read the presentation afterwards, but reliability and maintenance has received project financing in the region of £42 million. And if you see where that ranks on the general table of invest in terms of solving the problems within the networks, the challenges within the networks, you can see it ranks us pretty highly. In fact, it's next only to the future of gas, and as you probably know, that's the hydrogen play, but we won't go into that here. If we look at a DSO, that's the distribution system operator. Sometimes previously they've been called local distribution zones, LDZs. Then I'm focusing here in the big red circle in the foreground of this presentation, number 6. And the gas network is a play based on pressure. We'll probably start off upstream with Rolls-Royce RB211 jet engines compressors. We might use 2, 4, or 6 in quantity as a compressor train, But eventually, by the time it gets through the network, you've got industrial users. And finally, we reach the residential locations where the pressures are very, very low. And the way that the gas is moved throughout that value chain is based on pressure. So we build up the pressure and then we reduce it as we go through the network to the delivery points. If I was to take an LDZ, again, local distribution zone or a distribution system operator, lots of jargon, but basically this is how the network looks. So we have piping running throughout the UK in terms of the backbone, which is the national transmission system, and then we come off that into these local zones to supply into regions within the UK. And it's an eye test here, but this depicts where the compressor stations are, where the the power stations are, the CHPs. But all we're focused on here is the PRIs, which are the pressure reduction installations, and the PRSs, the pressure regulating stations. And although this is an eye test, you can get a feel from the triangles as to how many of these regulating stations there are. And this is just the northern zone of the UK. There are other zones, and of course this is pretty well how things run geographically around the world. So I won't labour that one. What does one of these things look like? They come in all shapes and sizes. Starting on the bottom right, that is a PRI, a pressure reduction installation. It's a master mechanical. It's valves, and where the blue dots are with the red circles, we're moving into that stream, that pipe run where we've got the pressure regulating. And as you can see, it's not particularly advanced from a controls perspective. There's very little electrical cabling, as you can see. They are purely mechanical devices. And even when the market's developed over the decades, and we've got some sort of redundancy, even 100%, that tends to be pneumatic controlled. It's pneumatics. So we're dealing with something here where there's not a lot of opportunity for connectivity in terms of supplies, even low voltage supplies, and hence energy harvesting. If we move to the top left, this is a bit more involved. It's a bigger system overview, because generally speaking, when it comes to the regulator stations, it's not just the regulators, it's the metering. And the metering is the, let's say, the cash register, if you want to be focused on that. And there's also a thing called a volume corrector, because as you know, natural gas is non-ideal. So you can see the volume corrector as the bureau de change. It'll convert your euros, your dollars, etc., etc. So if we go to one of the most advanced systems, and sometimes the infrastructure we have is decades old, several, but sometimes when new facilities are going in, you have the opportunity to be a little bit more advanced in terms of what you can do. And here we have what we call the monitor, active monitor setup, where a regulator in the green highlighted box or top left of center, the active regulator is working as it says active. It fails, it generally fails open. It allows more flow through or higher pressures. So then the monitor kicks in. It's just pneumatics. You can see on the right hand side, running down the slides, just pneumatics. And then you can run with the monitor. So you haven't got a shutdown situation, but you still have a run to fail. It is a run to fail situation. Monitors can be working on standby, etc., etc. We didn't go into the details, but basically that is as advanced as the global installed in base is in pressure control. If you don't have pressure control, you don't have your gas delivered. That's it across the value chain. There's been a lot of work over the years looking at SCADA systems and controls of that network, that bigger picture I showed you, the LDZ. And of course it's under control, of course there's controls. And if you were to focus on the regulator and the regulator stations, then you'll see there's much published. In fact, I got this particular one from 2019, which is probably the most up to date, but you'll find a great deal published. Here you can see on the risk aversion, everything was listed, but on the bottom I've added in what we're discussing here, which is monitoring. So if we were to go away from relying on that pneumatic setup, and bear in mind, there's a lot of install base that doesn't have that active monitor installed. It's a regulator, then you will run to fail. And if we were to think about looking at what we could do to predict the failure, so we're getting to a point where we can say you are heading towards a failure, but you are presently working. That's a tremendous advantage. And the challenge is, how do you install? Because if you take a low-cost sensor and then you say, well, I need some vast infrastructure to get these things powered, then you have to question, as a user, as an end user, a person that owns this infrastructure, you know, is the capital required justifiable? And of course, energy harvesting is a beautiful way forward. So I'm going to skim through these slides now as time progresses. And just to give you a quick feel without tremendous detail, vibration sensing on rotating machinery is prolifically published, and has proven itself. So here we see with these small green sensors in the foreground, and then there's one on the top left in the background there. We worked with a company called Everactive, and that's a vibration 3-axis accelerometer. Actually, it's a vibration sensor, and it is powered by energy harvesting, and that was a beautiful way to go. Hence the reason we started talking to that company, and it's been absolutely wonderful to work with, in the same way that we had that working relationship with Perpetuum. So they also had a thermal steam trap monitoring application. When you say, what's that got to do with what we're talking about here? Well, actually, nothing on a steam trap. But if you look at how they generated the supply to drive the box they had, they called it the Smart Sense node. It's on the left-hand side of this PowerPoint. In the middle, you'll see they used a TEG, and the Thermoelectric gen, of course, is again prolifically published, quite some history. So we were interested in what happened there with the TEG and self-powering this entire measurement. So if you bring those two together, you end up with a vibration and a thermal approach. And here we have the application, and here we built a 1-inch regulator. These things can be, in terms of pipe diameter, you could be looking at several feet, or meter or bigger too. This was simply done as a concept on a 1-inch pipe, and we used compressed air because compressed air is safer than natural gas. So if it showed any promise on compressed air, then the next step was, of course, to a real installation on natural gas. So here we asked the question, where do you place the sensing? So here I'm not going to look at the theory, what this sensor is doing. As I say, it's a 3-axis accelerometer, but we're not going to worry about that. Where would you place such a thing? Is it on the inlet pipework? Is it on the outlet pipework? Is it on the device itself, the regulator? Is it on the top of the device? Is it on the side? Is it on the bottom? Because there are different things going on inside that regulator, where you have these, let's call them segments or chambers. So we just applied these things everywhere we thought that might be of use, and we came to a conclusion for an ideal location. That was the result of the initial work there. What we did, and here I've removed some of the more informative, insightful numbers. This is early days, so we've got the pattern filing, but even so, these are early days. And what we've got on the left is, starting at the top is the baseline. So that's a healthy regulator. Through our exhaustive database, global database, and these things are prolifically installed in vast numbers around the world, we created the following. So starting at the top, we created known popular Pareto type approach failures in the field. And the following traces after the top one, 1, 2, 3, 4, 5, 6, 7 down, they're all following the Pareto as to the classical fails that we've noted in our historical database, and we've simulated them or created them to see the response. And then on the bottom trend, we've gone back to baseline, because it's always good with any testing to start with base and finish with base. If you move to the right, we are moving with just one individual trial, one failure mode. And you can see again, we have the before and after, or the baseline. And we were finding some challenges. Now, it's obvious on the top and the mid traces on the right hand side. It's just the peak of the output from the accelerometer. If you look at the bottom trend, that's getting to be somewhat challenging in terms of being able to clearly state that the sensor is capable of detecting an issue, a problem, a potential fail. So we had some interesting time with this. We found it's also a function of flow rate, but even so, good results. What's even more interesting, and hence the energy harvesting, is that it's a non-ideal gas, and the non-ideal gas has its boundaries, its phase boundaries, and depending on what you're doing with pressure, there'll be certain temperature correlations, and you can move in and out of different phases. So if we were to see that the regulator is a pressure reduction device, and quite often that reduction creates a temperature drop, and that drop is the Joule-Thomson effect. Again, I don't need to discuss that one. That goes back to the 1800s. So you know, it's well known, well defined, plenty of math and proof out there. But basically, you drop the pressure. There's no rules of thumb. You know, a pressure drop gives a temperature drop, roughly, without the vast math. And here you can see some real life effects. The photo in the top right hand side, that's being operated outside of its intended design, and you can see the extent of the pressure drop. It's actually pulling moisture out the air, and you've got this ice building up. And what's even more telling is on the bottom right hand side, I wouldn't say this is in a desert, but the sun's certainly shining. You can see the shadows. You can see the you know, the sort of dirty, soily, warm deposit and the rusty pipework. But what's interesting is that the regulator, the round dish, is dropping pressure. And look at how we've created such a pressure drop that the pipework is chilled, pulled the moisture out of the air. Now we've got freezing, water freezing on the pipe. Amazing contrast when you see that the sun's shining on the regulator, the red dome. You can see the shadows from the pipework. You can see it's a dry, aridy sort of air environment by the sub-base there, but still we've got temperature drop. Now then, if we drop the temperature, it's a very simple rule of thumb for a bar, a temperature drop. We can move into the world of TEGs, and we can then consider self-powering the vibration sensor. So it's good to have the vibration sensor, that's the predictive element, but you have to power it. And bear in mind from those early photographs, these things are quite isolated, were never intended, ever, for numerous decades, to be powered in any way. And any smart approach to active monitoring was pneumatic. So, you know, to have this thing self-powering would be absolutely awesome. And the TEG's obviously the most viable way to go. So this is an extract from an 80-page document I spun up some years back looking at various energy harvesting approaches, of which the TEG was one. And we decided to go forward with that approach. So we went back to Everactive, we looked at the TEG, and we thought, why not apply the TEG to this application? It's not a steam trap, so it's not heat, it's the opposite, it's cooling, it's cold. But for a quick look, we thought we'd leave it as it is, but bear in mind that, you know, we're not going from hot to cold, we're going, we're doing the opposite. We're not measuring a hot surface, we're measuring a cold surface. So we started to track what off-the-shelf TEG could do on this application, and we found that there's a wake-up point of 11.5 degrees C. There or below, it certainly spun into life. And the cycling up and down here on this chart, which is just time against temperature, we were manipulating, activating the regulator, and that in itself allowed us to control the flow rate and across the pressure drop and therefore the temperature. So we were able to cycle this and understand how the TEG would perform, understand, you know, where the temperature starts rising here at each test event, each trial. We were able to monitor that, see where it stops working. So we knew where it stopped, we knew where it started to perform. And bear in mind, this wasn't optimized because, you know, at first we were without a saddle, but, you know, then we tried a saddle that was available, and that was in the previous slide. I'll just flick back there quickly. You can see the saddle in the middle, red highlighted zone, TEG on the top, saddle on the bottom, just about to be mated to the pipe. So we took that. It wasn't specifically made for this, but we took it, and this is the result we got. So we were quite convinced that once we knew where the wake up started, that temperature would then tell us the pressure drop. With the pressure drop, we could then determine if this would be a success or not. So that's how it worked. So what's happened since then? Well, that was over the period 2018-2019, and as I mentioned to you, the TEG was not optimized for this application. So we've been concurrently working with our Honeywell Aerospace colleagues, hence the reason for the F-35 picture early on from their business. And this is what our TEG it's actually a working device, but it's still in our labs. We've moved from the drawings to the real thing, but we've got this compact TEG. As you can see, it's bolted on this circular tube, and we're building up our own TEG to be the power source, and having some success. What's even more exciting is we look towards the photovoltaic options, and I personally believe that Lightricity have an excellent product offering here, solution. But I'm not going to talk about that because you have a speaker from the very company. So we envisage this ending up with a dual approach, the TEG and some sort of excuse me, photovoltaic. Why do I hesitate a little on the light side? Well, what you haven't seen here is that quite a number of these can be buried in buildings or buried underground. So maybe the light wouldn't be as widely accepted as the TEG. So that's where we got to. That's the working end, should we say. Now, if we come back through to an enterprise zone, we then built this unified control instance. So if you're familiar with your PLCs and your RTUs and ultimately your SCADAs and your DCSs, we brought in our Experian software offering. It's our DCS. It's somewhere in the region of 2 billion of the 5-something billion business that we sit in here, out of the 40-something plus billion sales. If we see what we spun up, it's here in the center. So we've got the prognostics, so predictive. We've got the performance modeling. We've got machine learning and AI, all that good stuff. That's all about residuals, as you know. Any AI approach is residuals. We've got this pressure regulator PRS development KPI that we came up with. The opportunity value, well, that's all about the math of what you do and don't do on your CapEx, OpEx discussions. And recommendations. Now, the recommendations engine that we're building, that not only is working with the predictive side on the left of the screen, but the recommendations on the right, particularly on the bottom right of that black screen area in the middle of the slide, it's a recommendations area, and that's where we're being very specific as to what is being predicted in terms of failure. And that takes you back to the early presentation where I disguised those frequency spectra, where we had the baselines and then the various faults in between. So we spun this up so that from the end user's perspective, and this is an enterprise view across the whole DSO, or the LDZ, the distribution customer, we're giving them specific recommendations, go-dos. So this regulator will fail on this part at this time. And with the machine learning and the AI, we believe we can get to, certainly from weeks, 1, 2 to 3 weeks, we are seeing some promising results. It's all about the models learning, but we're hopeful to get to 2 months advance notice, 2 months. Which, when you consider this as a run-to-fail historical approach, that's pretty pretty good. And to be able to then say exactly what's going to fail, that means the end user better understands the failure mode and the priority of that failure mode, and then any safety implications. So that leaves me to say thank you for your time and attention. And I hope you found the application side of energy harvesting useful. And at that point, I will stop sharing and I shall hand back to our host.
Thank you very much, Martin. Are there any questions from the audience for Martin? And if you do have questions, can you use the raise hand button? So in the center bottom, you can see 4 buttons, one which is raise hand. So if there are any questions. Anyone? Maybe everyone's stunned into silence by Martin's presentation. I see. So, Simon?
Hi, yeah, it's Simon Yarwood from Knowledge Transfer Network here. Really good presentation, really interesting and impressive set of solutions. One thing, and possibly might sound a bit rude, don't mean it that way. What do you think's taken so long to come up with implementing these, or sorry, for customers to come round to the opposite? So you were saying there was an opportunity in, you know, thousands of units and all these different bits all over the world, and you know, this community here has known about the potential for such a long time. I'm just interested what you think was the trigger point, particularly for that need for them to come and ask for it, as it were.
Yes, no, thanks for the question, Simon. I hate to say it because you hear this all the time, but it's the 2020 scenario. There's been nothing in the industry for the past decades that has been as impactful as the 2020 year globally. And one of the overwhelming reasons that Honeywell has been every company's impacted, but not as badly as we thought we would be, is because we started energy harvesting a long time ago. You saw back to 2005. Yeah. Same with what we call remote operations. We introduced that around about the 2016-17 period. Again, no tremendous uptake from the customer end, but when we came into early 2020, my golly, we have been swamped, absolutely swamped with remote operations requests. And what the customers are telling us is that they have been compelled to go down that road because of the 2020 pandemic. They were compelled. Having been compelled, they've seen the advantage, and having seen the advantage and the cost impact in terms of savings, they're telling us, you know, there's no going back to what we used to do. We're moving forward in this new way. And it's been that shake-up, that global shake-up in 2020. I hate to say it because it's getting, you know, a lot of everybody's blaming everything on COVID these days, but it has been in this case the decision maker. And this particular customer, if you're interested in numbers, Simon, would you like me to give you one or two fiscal numbers? Would that help?
Definitely. No, that's, for me, helping companies realize the potential of this stuff. If people can give me numbers, it's really helpful.
Well, we discussed this with the client and they offered $50,000 per station. They've got 200 as urgents, 1,900 that they'd like to tackle. That's just them. This is a customer in a country. There are many, many customers who would need this, and we've already started getting inquiries. What they're saving is run to fail. Run to fail, it can be a safety issue. Sometimes it's the safety issue that drives, not the OPEX. This one's safety, because when you run to fail, these things tend to fail open. When you fail open, you overpressurize. If you overpressurize, you can move into the areas of pipe fractures. And there's been some very unfortunate situations with loss of life. Very extreme. You can name probably 2 around the world. So that's that one. And the truck roll, they go out on calendars at the moment. So if you take that quantity number I gave you, that one customer, They roll a truck with a man, and he uses his sight and his hearing to determine what's going on, and they roll him out every month to each one of those installations. With this opportunity with harvesting, that got us the power for the sensor. With the sensor, we've got the insight. With the insight, we reduce the truck roll to nothing more than repair, or swap out before repair. And the cost of that was in that 46 million a year that they spend rolling out. So we believe that it's not unrealistic to be looking in the realms of saving 3-4 million a year on your OPEX, and more actually, depending on your infrastructure. So they're the numbers.
Wow, brilliant. No, thank you very much.
Yeah. Most welcome. Thank you for the question, Simon.
Sorry, I'm just mindful of time. I see that Ali has hand up for a while, so maybe just a quick question and a quick answer if possible. I do want to move on. Ali, do you want to ask a question? Okay, maybe Ali can catch up with Martin later privately. I'm just mindful of time if we can move on to the next talk. Alex, are you ready?
Yes, good morning. Let me just share my screen. Just give me a moment.
Yeah. Thank you, Martin.
Okay, do you see my screen now?
Yes, perfect. Thanks,
Great.
Alex.
So, good morning, everybody. My name is Alex Weddell. I'm from the University of Southampton, and I've been working in energy harvesting for about 15 years. We are small partners in this project, which is focused on enabling access to European infrastructure associated with energy harvesting. So in this presentation, I'll tell you a bit about this scheme, how you can get free access to the expertise and facilities of our partners, and I'll introduce a few case studies of projects that have been through this scheme already. So the background for this project is that there's forecasts of massive growth in IoT devices over the next few years. I mean, obviously, we're probably not going to get to 1 trillion by 2025 now, but we're well on the way to that number. And clearly, we don't want these devices to be powered by batteries. So the motivation for this project was to assist companies and universities to make the next step in enabling energy harvesting powered devices. So we're looking to work collaboratively with organizations outside the project to help them to overcome technological challenges. So the enable solution is we have funding of about 5.2 million euros. We've built a network of stakeholders, I guess similar to the UK's energy harvesting network. We have about 500 members already signed up to our network. And we're looking to create self-sustaining solutions for powering the Internet of Things based on energy harvesting, energy storage, micro power management, including power management ICs, and also system integration. So some of the brains behind how to design appropriate energy harvesting systems for a particular application. So looking at the partners on this project, Southampton is a relatively small part of it. So the project is run by Tyndall National Institute over in Ireland. We also have partners in France, so that's CEA, IMEC from Belgium, Karlsruhe Institute of Technology, and 2 of the Fraunhofer Institutes in Germany. And we have Bologna, Torino, and Perugia from Italy. So the main activities under this project can be split into two categories. The first of which is going to be the most interesting to you as a potential user. So we facilitate fast-track access to expertise in energy harvesting and also to our cutting-edge lab facilities. So we've got over 130 researchers associated with this activity, and we are making about 2 billion euros worth of infrastructure available. So we've got a lot of specialist equipment which is being made available through this scheme. Access to this scheme is completely free of charge, and in fact, if your use of these facilities involves travel to one of the Enables partners, then you can claim back some of your travelling expenses in order to do that. The other part of the project, which I'm not going to be presenting today, is on joint research activities between the partners. So the idea of this is that we are innovating in the fundamental technologies and also doing some community building and standardization activities as well to drive things forward. Right, so I'm just going to go into a bit of detail now on our offer for the Transnational Access Scheme. So that's the scheme that allows you to get access to these facilities. So this is split into energy harvesting, energy storage, micro power management, and systems integration. So on the energy harvesting side, Tyndall in Ireland are offering expertise and facilities associated with piezoelectric MEMS device design, fabrication and characterization, electromagnetic vibration and hybrid platforms, and thermoelectric materials and devices and characterization setup. CEA Lytton in France is also offering facilities in thermoelectrics, but they're looking at material modeling and screening, as well as numerical simulation and design of energy harvesters. They also have expertise in bulk or thin film thermoelectric harvester advanced characterization. Fraunhofer IIS have a data logging capability that they're making available through this scheme, and that allows you to see how much environmental energy is available in your intended deployment environment, so that we can look at how much energy you could get from a harvester and what type of harvester would be appropriate for that application. The other Fraunhofer in the project, Fraunhofer IMS, has a thermoelectric generator testbed. They have expertise in photovoltaic harvester design and processing. They also work in RF harvesting design and processing. And they can also do some work on design and characterization of energy harvesting systems. Lastly, IMEC in Belgium have expertise in RF power transfer. And you can see an example of one of their systems here. Okay, moving on to energy storage. So that's the second of our themes through this program. So both Tyndall and CEA Leti have expertise in electrochemical and thin film batteries. So Tyndall are looking at electrochemical energy storage based on Tyndall's smart materials and test structures expertise, and some electrochemical cell batteries and solid state energy storage. CEA Leti have material and process evaluation facilities for thin film solid state rechargeable micro batteries, and also similar expertise in electrochemical energy storage. Okay, moving on to the next theme, micro power management. So Tyndall have expertise in power management ICs, and they're making that's available through this project. So they have low power analog and mixed signal design facilities for IoT building blocks. Fraunhofer IIS offer design and characterization of micro power management systems. IMEC in Belgium, I don't know if you've already seen about this, but this is their music chip, which is intended for medical applications. So that is a low power chip solution for healthcare as well as general sensing applications. And that could be adapted to a range of IoT deployment environments and sensing tasks. So effectively, they have toolboxes for those building blocks for IoT applications. Fraunhofer IMS have a thermoelectric generator testbed that's being made available. The last theme is system integration. So Tyndall is offering access to their system integration tools. They enable simulation, optimization, and evaluation of IoT power systems in wireless sensor networks. This includes a simulation and optimization tool, as well as hardware platforms that they have available that enable a rapid prototype to be produced. Fraunhofer IIS in Germany have a facility to characterize energy harvesting sources, generators and systems in environments replicating, in simulated environments representative of vehicles and large machinery, etc. So there's quite a wide range of facilities available. You can find out a lot more detail about these through the Enables website. So you can jump to the Enables website, and I'll drop a link to that into the chat shortly, and you can see the capabilities of each of our partners. So next, let's look at how you can access these facilities. So what does a typical access request look like? Well, firstly, it must be transnational. So I know that we're joined by a lot of attendees from outside the UK today. The key aspect here is that you must be requesting access to a facility that's not in your country. So for people in the UK, that's fine. All of the organisations that are offering transnational access are outside the UK. If you are outside the UK, don't go for an organisation which is in your country. The access may not include a visit, so we have facilities for remote work to be carried out. So, for example, if you just wanted one of our partners to build a prototype for you, and you're happy for that to be done remotely without you visiting their site, that can be arranged. Or if you have a sample or a prototype device and you want some testing to be carried out on that, you can just ship it to our partners, and we can just do a test on that. Normally, the projects that we offer through this scheme are feasibility studies. They may be testing samples. There may be a proof of concept prototype put together. Typically, our projects that we run through this scheme represent about 2 to 4 weeks of effort for staff from our partners. It is occasionally permitted to run longer projects than that, but please have a chat with us about that. I know that some projects, particularly those involving IC design, tend to be a lot more involved and require more effort. So what do we look like when we're evaluating applications to this scheme? So firstly, we're looking for innovation. So we're looking at whether it fits with the expertise of the of the organisation that's requested the project. We're looking at whether there is an advance over the state of the art being proposed. We're also looking at the proposed outcomes. So as part of this process, we ask you to think about whether the work could be published or how it could be taken forward by a company. And lastly, we look at whether the use of the advanced infrastructure is justified. So it's a six-step process from thinking about an application through to the end of a project. And I'll go through that step by step for you now. So the first step is to sign up, and I'd encourage everybody to sign up to the Enables network. And as I said, I'll stick a link for that into the conversation window at the end of my talk. So you just submit a sign-up form, so that enables you to join the network. We have a newsletter that's sent out every 3 months, and we won't spam you, we won't send your details to anyone else. This is just for use within the network. And in that newsletter, we include updates on technologies we have available, events that we're planning, and general news from our partners. So once you're a member of the network, you can submit an inquiry about transnational access. So you can submit a technical inquiry with details of what you'd like to do, and then you'll be linked up with an expert in that area to discuss it further. And then you need to submit a formal application. I say a formal application, it's a relatively short form. I think it's only about 4 pages long, and it's asking you the key information that we use to evaluate whether it's suitable. And you'll be assisted by the proposed access provider in preparing that application. The next step, we send out the application to a small selection panel, and we generally turn around applications within about 2 to 3 weeks. So it is a really quick process. We will either approve a request, we will request clarification, or we'll reject it. And I should say it's very rare for us to reject an application. But a very, very high success rate in applications to this scheme. So it's not a competitive process as such. There's lots of funding available at the moment. So if you apply to this scheme, you've got a very good chance of your projects being approved. Next is access. So you can either access the facility remotely, or we can do some testing on a sample for you, or perhaps produce a prototype. So that is the access to the proposed research infrastructure. And then at the end, there's a reporting requirement. So for universities and for large organisations, we expect there will be some dissemination in papers. So we expect you to publish results. SMEs are exempt from that requirement. We also expect you to provide a report to the interface team, and at that point we will reimburse you for the permitted travel and accommodation expenses. As well as the physical access to facilities, we also offer virtual access, and we offer vibration data, both from the NIPS lab from Perugia and from the Energy Harvesting Network data repository hosted at Southampton. It's a much quicker process for getting access to those databases through Enables than the transnational access scheme. Okay, so just looking quickly at some examples of past projects that have run through the scheme. The first of which was with a company called LV Logics, based in Ireland. They provide monitoring equipment for grain and pellet silos. The level of material in the silos is measured through an optical sensor. So obviously you have to power that optical sensor, but also it has a cleaning mechanism. Their system was hardwired, but through one of these projects, they evaluated the potential for powering it from energy harvesting. So they worked with one of the Fraunhofers, and there was a feasibility study followed by a proof of concept demonstrator. The next that I'm going to tell you about was from a rail company in Austria. I think looking at the side of this train, they may have seen Boris's bus. So they wanted to enable GPS tracking of rolling stock. It's a big issue. Rolling stock can be located anywhere on the rail network, and it's quite difficult to track it down. So they wanted to enable GPS tracking for rail applications, and ideally wanted it to be powered from vibration on the trains. So they've actually run 2 projects with us. The first of which was to evaluate how much vibration there was on various parts of the train. And then there was a follow-on project that integrated a vibration energy harvester with a GPS tracker. And this is what they thought about the process. And the last project that I'm going to tell you about was with a US company called PowerRocks, and they had a prototype smart patch device, which was to be energy harvesting powered, but they didn't really understand the power usage profiles of the various components on their system. So they worked with Tyndall, and Tyndall characterized the power consumption of each part of the circuits and generated detailed models for that, so that PowerRocks could then go forward and develop their design further with confidence that the changes they were making were not going to exceed the energy budget that they had available to them. And here's a quote from PowerRocks. They were extremely enthusiastic about it. Okay, as well as access to facilities, we also participate in community building. So we've run a number of webinars over the last few months, and they're all available on our YouTube channel. We also sponsor certain energy harvesting focused workshops and events. We have inputs into some standardization activities. I'm just going to mention our winter school. So the winter school is sponsored by Enables, and it's being coordinated by Perugia. Perugia usually run a summer school that is based in Italy. It has a 10-year history. It's had something like 430 attendees in that time, but this time it's going online as a virtual event. It's open to anyone who's interested in the topic of powering the IoT, and you can sign up for free via a web link that I'm going to put in the conversation window shortly. So there'll also be the opportunity to display posters at this event as well. So this is the preliminary agenda. It's taking place on the 15th to the 18th of next month, and it's running in the afternoon on each day, UK time, between 2 and 5 p.m. So we've got a wide range of topics being discussed, including fundamentals of energy, looking at nonlinear vibration energy harvesting, that's by Perugia, radio frequency energy harvesting by the Fraunhofer Institute, PV energy harvesting by University of Torino, transient computing, sorry, intermittent computing, that's being done by me, nonlinear power management for piezoelectric transducers, that's by Bologna, batteries and beyond, that's from Milano, system design, considerations by Tyndall, and a hands-on session with the Wise Power company, which is based in Perugia. And then on the final day, there are posters and flash presentations. So if you're interested in this and you'd like to learn more, I'll pop a link into the conversation window at the end of my talk. So that concludes my presentation. Thank you very much for your attention. I would encourage you now to sign up to the Enables network, and I'm just going to pop my links into the chat, into the conversation window for that. So does anyone have any questions? Martin.
Hello, Alex. Yes, quick one. The testing prototype, you mentioned vehicle and industry on a sort of manufacturing scale. I noticed in the slide it looked like a rather large square meterage area, almost some sort of environmental chamber type approach, rather than the classic bench or table in a lab. Would I be right in thinking that that facility where you mentioned the vehicle industry testing is of quite some square meterage, and it's a complete, almost an environmental chamber?
I believe so. If you'd like to know more, submit an inquiry through the Enables website, and as soon as you do that, you'll be contacted by a member of staff from Tyndall, who's employed full-time to manage the Access programme. So he'll know the details of what's available at each of the partners, and can link you up for a discussion with them before you go forward to a formal application for Access.
Great, thanks, Alex.
Thank you.
Alex, I think there are a couple questions in the chat box.
Okay, so thank you. So the first one, how do you deal with IP? Okay, so there's a negotiation around IP at the point where your project is approved to go forwards. I must admit I'm not familiar with the exact details of that, so I won't attempt to answer that. But again, submit an inquiry through the Enables website, and that can be answered. We don't publish a list of Enables network members, so we don't have a website with all of our members listed. I don't think we have permission to do that. So it's a bit different from the UK Energy Harvesting Network. And the last question is about who can sign up to the winter school. Yeah, it's not just students. It's aimed at people who are researching into energy harvesting systems and are at an earlier stage in their career. But yeah, it's not just students at universities. It could be people researching into this area in industry as well.
All right, thank you very much, Alex. And
Okay.
I think there are no further questions. Yeah, once again, thank you very much, Alex, and just being cautious, mindful of time. Jonathan, are you okay to? So our next speaker is Jonathan Siviter. Hello, Jonathan.
Yep. Hello. Morning, everybody.
Hi. Morning.
I'm just getting the presentation together.
Are you able to
Just
find
find it.
the button? Yeah, perfect. Thank you.
Yeah. Oh, my screen share now is blanked out. Hold on. I'll make a quick start. Hopefully it'll let me use it in a second. So I'm Dr. Jonathan Siviter. I'm from SME Thermoelectric Conversion Systems Limited. We are based in Glasgow in Scotland. We spun out of Glasgow University back in 2015, and we've been working in thermoelectrics, for quite a while now. I did my PhD and postdoc at university focusing on thermoelectric coolers, and we've got some expertise in power generation that we've used in various projects over the last few years in energy harvesting, It's not my first presentation at this conference. I've given a few in the past, but I've got some more new projects we've been working on and some new partners we've been working with in generating some power from our thermoelectric devices. And this is still taking a minute to finish uploading.
Jonathan, are you using the share file option? Okay.
Yeah, it's ground to a halt.
You can share screen instead, so it will be a bit more quicker.
Ooh. That's probably easier. The share now button is completely frozen out on my system. I can't seem to do anything. How do I share screen? That's probably the fastest thing to do.
I think go back to the main share content area. There's a share application /screen.
Yep. Got it. That's much faster. Application window. There we go. There we go. Okay, thanks. Sorry, everybody. Back in business now. So for this, I'll give you a quick overview of TCS, even briefer than I've just done, and then go into a bit more detail on the couple of energy harvesting projects we've got running at the moment, and then talk a bit about test and characterization systems and services we offer, and then finally I'll finish off with talking briefly about our cooling systems. So, as I said, because we've been in working on thermoelectrics for a wee bit of time, we've got kind of 4 or 5 different areas that we focus on. So from power generation side, which is, I guess, most interest to this network, we have a focus on the heat exchangers, the thermoelectric modules that you can buy, and specifically the power converters. And that's probably where our most active area is, in the different DC-DC converters, all from bespoke technology and systems that we've built and developed in-house here. Second is on test equipment. So this varies drastically from actually testing physical thermoelectric devices through to software and backplanes that you can use for different power converters, and also the whole system so including data acquisition, logging, characterization, that sort of thing, and all the systems that go alongside that too. In addition, we don't just sell these as bits and pieces off the shelf. We also do the testing in-house. So we have functional testers. We have got a couple of test rigs that we can use for testing thermoelectric generators and also thermoelectric coolers. And finally, we've been working in thermoelectric cooling for a time as well, and got some new cooling modules, and also kind of the full system consisting of the heat exchangers and also the actual controller that will create the delta T or the cooling capacity you require. So in terms of energy harvesting, we focused on what are multi-generation systems. So these are systems where the TEG is working in parallel or as an additional generation source to another system. So we've got 2 projects that use solar as the main energy source, and TEGs are an add-on to that. So the first project is a passive solar pump with power generation, and the second is a concentrated solar plant, again with a power generation add-on module. So a little bit about the modules that we use. These are optimized for really high temperatures. They're standard bismuth telluride modules at the moment. They have a maximum continuous hot side temperature of 340 degrees C, but a maximum intermittent temperature of 400 degrees C. So this is fairly unique. We found in the market that they can withstand much higher temperatures for for short periods of time. When I say short periods of time, I mean you operate it for maybe a minute or so at that high temperature, and then as long as it comes back down to about 350, 340, device characteristics aren't changed. This device can generate up to 20 watts of electrical power at 16 volts open circuit and works with our maximum power point trackers. We also have an addition to this TEG, which is our monitoring pellets. So these are essentially a set of couples inside the device that are excluded, 2 couples out of the 200 odd that are in there that are excluded, that we use them to operate the DC-DC converter at high efficiency. And I'll go into a bit more detail about what that means in a second. So this is our range of maximum power point trackers. They range in size from very low power, half a watt to a watt, up to higher powers of 100 watts and 200 watts. Of course, it depends on the system you're applying them into. The AM2 is quite useful in that it has a very low turn-on voltage of just 80 millivolts. However, the micro harvester, although has a slightly higher input voltage minimum turn-on, the output power is a lot higher. It's up to a watt output power, and in fact has a little coin cell operated on board as well, so that you can actually use this as more of an intermittent charger. You'll see the AM2 also has a little supercapacitor on board, so again you can use this to where you've got intermittent delta T from the thermoelectric device that can be used to then store charge in the supercap over time, or in the little lithium ion cell over time, and then when you wish to do a data transmission or something that takes a high amount of electricity, then you be stored in the battery or the energy storage device to make that transmission. The KM2 and the KM3 are slightly higher power devices. These are more traditional sort of standard DC-DC converters that operate from a very wide range of input voltages and to a fixed output voltage. These are previously been developed for needing a lead acid or a lithium ion battery at the output, but we've just finished development of AC output, so you can tie these converters directly to the grid. You don't need to, you need an inverter, but you can use this converter off the shelf for that. So a little bit on the first project, which is the passive solar pump and power. This is the system diagram. This project is in collaboration with the Centre for Global Equality, Bahir Dar University in Ethiopia, UCL, and Economad Solutions, which is a spin out from UCL. As you guess from having a Bahir Dar as university, this is a project focused in Ethiopia, where we're focusing on rural access and improving rural access to facilities and to energy. So a lot of the object of the project really is to develop an alternative form of energy generation. So this is using solar thermal. The idea is that you've got 3 different technologies being combined here. So this solution is really, because it's targeted at off-grid communities, we're also looking at places where the average solar irradiation is very high, and basic needs, of course, are at the greatest. In these places, the technologies to be developed consist of an integrated innovation package, which represents a unique collaboration between British and Ethiopian organisations. The solution includes the following elements. It's a passive solar pump, which is a patented British innovation developed by Economad Solutions, which is essentially a thermal engine that pumps water around the circuit without any moving parts, nor has it any electronics or photovoltaics. It also captures heat directly from the sun and converts it to a vapor pressure through unique expansion chamber. In turn, this pumps water to a various height, up to about 10 meters as proposed in this project. So at this point, this is an early stage prototype that's been under test at UCL. The kind of the heat or the thermoelectric part of it from the TEG is from our side. So this is done to convert the DC power that's available from the temperature difference between the heat collected from the solar collector and the water circulating in the expansion vessels to generate DC power. And the aim of this is to produce between 5 to 10 watts of electricity. The third part of this is the turbine, is the micro turbine generator. So this is taking water essentially from the header tanker, from a top pond down through down through the system and outputting it into a bottom pond, or sort of a reservoir at the base. So the idea is that the top pond is an overflow. When the sun's shining, you've got water being pumped up to the top reservoir, and then an overflow collecting in a top pond, and then as water drops back, the turbine kicks in and can generate a small amount of power. So this is our proposed test setup. Of course, COVID has impacted it and has made travel impossible at the moment. So the idea is to install a system on a 7-meter tall structure, so which the passive solar pump can pump up to 7 meters. The TEG then collects energy from the collector system and converts it into DC power. And again, the micro turbine is creating additional energy. We're only talking the same sort of 5 to 10 watts from the header tank as it collects into the pond at the bottom. So the aim with this is to actually generate small amounts of power. We're not looking for kilowatts. We are really only looking for 10 to 20 watts of DC power for mobile phone charging, and for some lighting. The second project is this concentrated solar plant, again with some power generation. This is developed with Cranfield University and consists of a parabolic trough. You've got a receiver tube at the focus, and oil is pumped through this and heated. This oil can then go straight onto a cooking surface. So this is really focusing on a clean cooking application, where we're avoiding the use of fossil fuels in the cooking process and converting it to using a more green solution, where although there's an oil loop, it's traditionally just a cooking oil, and this is then kept in a closed circuit for transporting heat from the solar energy plant through to the thermoelectric part. And the thermoelectric part is taking its heat from the oil through a water circuit that gives you the delta T, and that delta T is then producing the DC power. So what's unique about this system, I guess, is that the system can be moved around, and it actually looks fairly portable. So although the application again is rural and off-grid systems, it would also be suitable in sort of emergency relief and disaster emergency support. Again, we're not targeting a huge amount of power. The main focus of this is actually for a clean cooking solution. And we're looking at producing about 20 watts of DC for mobile phone charging and for lighting. So those are the two energy harvesting projects we've been focusing on for the last wee while, and we've got another wee bit of time left on the projects. What it also lets me talk about is the testing and characterization that we as a company are capable of, and I guess what I'd like to get across to you is that we are very much agnostic about the type of material that you want to test. We've got developed various testers for different companies and different materials and different universities. So really down from the very small 3mm by 3mm size of TEG. This was for a silicon nanowire thermoelectric device. You can see in the image, we've got a stepper motor that provides pressure compensation and control over the applied pressure and the clamping to the thermoelectric device. And we've also got a heater for the hot side. Again, this system, the cold side of the system is actually a closed loop water circulator with a thermoelectric cooler as the cold side. So we're not needing a separate chiller. So a single TEG is located in the center of a 40 by 40mm PCB mount. That means that a sort of carrier plate can be produced and then loaded into the tester to make it easy to input and remove from the system. You can test up to 4 tags in a single test. We've got a specially designed hot side that contacts just the face of each of the thermoelectric devices under test. Not just testing of generators, but we also offer cooling cooler testing. So this was for a customer switching types of devices, so moving from one manufacturer to another, where there was a concern about the performance of devices. Even though on paper in the datasheet they looked like they would perform exactly the same, what we actually found was that there was a slight degradation in performance when we tested a large number of devices in a direct comparison between cooling capacity and applied current. So we essentially did a temperature cycling system for each of these devices, so we could test large numbers at a time. We first did a sort of an initial characterization to understand the baseline performance, which is the system you see in the center of the screen here. And then we changed this to test 20 devices in parallel all at the same time, so that we could cycle many at the same rate, at the same temperature, and discover any differences. So from the graph on the right hand side, you can see that the orange curve was the original device that they had specified, and the blue curve was the new device that they wished to use. The error bars sort of denote that although there is a slight drop in performance, the number of devices that we tested meant that the error bars showed that you could have a similar cooling capacity, although it was slightly reduced to what they originally had. Finally, I want to go into detail about a high accuracy tester we're finishing development of at the moment. We're really down at the very low voltage and very low current values to characterize. This is built on a 7x7 2-centimeter block, with clamping up to 2 kilonewtons, a high hot side up to 700 degrees C, and a controllable cold side, depending on what your testing system would require. The system uses thermocouples, but we can switch to using RTDs if it's more in line with what you're looking for. Again, this is on a system that uses a PC or Excel outputs and diagnostic software. This is seen as a benchtop instrument. Again, no separate vapor compression unit needed. We use thermoelectric coolers to provide the cooling for the cold side. That very quickly brings me to the end of my talk, and a quick thanks to my collaborators on these projects. And I've got bags of time for any questions, if anyone has any.
Thank you, Jonathan. Anyone have any questions? You can either type the questions in the chat box or raise hand if you would like to ask. Well, I guess no one has any questions at this point. I'm sure Jonathan will be happy to take any questions afterwards.
Yep, of course. I'll put my email address in the box as well. If anyone has any questions, you can email me too.
Yeah, appreciate that. Thank you very much, Jonathan.
Thanks, Jerry.
And for anyone who just joined, if you scroll up to the very top of the chat box, there is a link to the agenda, not just for today, but also for tomorrow and day after. I just want to highlight that on the last day on Friday, we do have a panel and audience discussion, which all of you are very welcome to join the discussion. Okay, so we're a little bit ahead of time, and I think we can move on to the final session for today. Matias, are you ready?
Oh, we actually do have a question for Jonathan, I think. Sorry, Jonathan.
Hello.
Yeah, there's a question in the chat box for you, I think.
Oh, excellent. Can you give more information on the TEG on the top of the exhaust gas type of applications, prototype, and rollout? Yes, so the exhaust gas TEG we actually have used in a couple of projects. The first was on a steel processing plant. So this was taking exhaust gas stream at about 300 degrees C onto a series of 16 thermoelectric generators, and the output was put into DC-DC converter, and we were producing about 200 watts of power. So that was the one application. The second, we actually were about to test this on a boiler unit. Again, like the exhaust gas is about 200 degrees C, so we're expecting a much lower output power. Hope that answers your question, Fabrice.
All right, thank you very much. Thank you, Jonathan, once again. Matias, are you okay to share your... Yes, perfect. Would you like to share screen, your presentation?
Yeah. How can I share my screen? I think it's...
So on the bottom right side, there is share content. And then click on that, there's the share application / screen.
Okay. Okay.
Thank you very much.
Okay, so can you see my screen?
Yes, but
I don't know which screen I'm sharing. I think I'm sharing the right one, isn't it? Can you see the harvester, the ball and the boy? Yeah, I think
with
you can.
water, right? Yeah.
The presentation, yeah. So I'll go ahead. So hello everyone. First of all, thank you to inviting me to this session. It's a pleasure for me to share my work. As I'm the last one here, I will try to be a little bit dynamic. So I added many videos and many animations to my presentation. And as I didn't know the background of the listeners, I just presented some of my material. But if anybody wants further information or further results of what we did, just contact me, and I will be glad on sharing my results. So, my name is Matias Carandell. I'm from Spain, from Universitat Politècnica de Catalunya, and I work in the topic of kinetic energy harvester systems for to be embedded on drifters. This is a project which is held on the European-funded project called MELOA, which aims to develop a new family of wavy drifters. The content of my presentation will be the following. I will start with an introduction of the marine observing systems. Then I will talk about the kinetic energy harvester device that we have designed. Later, I will talk on the power management on this system, followed by the design of a real-time power monitoring the drifter. And I will finish with some of the tests that we have already developed. So, to start with, did you know that 95% of the ocean is still unexplored by humans? This is a very highlight. And more information about this is 50% of the oxygen from the photosynthesis comes from the ocean. And also another highlight is 90% of the heat from global warming has been absorbed by the ocean. This different sentence bring us the importance of providing resources to monitor the ocean, to monitor how the health of the ocean is. A Lagrangian drifter, maybe not everybody here know what is it, is a low-cost, low-power oceanographic autonomous device which passively follows the currents while monitors some sea parameters. They can be like current flow, temperature, salinity, or other parameters on the sea. They are used on climate research, but also on oil spill tracking or rescue operations. As these drifters may be for a long time in the sea, maybe for up to 1 year, one of the big challenges is autonomy, as well as price or robustness, but our main topic here is autonomy. I've showed here some of the commercial solutions that can be found on the market, as the SOFAR, spoon drifter from SOFAR from USA, or the solar drift from Fastway. All of them, as you can see, use solar solutions. For example, the spoon drift from SOFAR use 5 2-watt solar panels, which they say that can provide unlimited autonomy, obviously in propitious solar conditions, because we highly depend on the sun here. But solar panels are not the final solution for the drifter's autonomous problem. Why? When we use a drifter, we want to monitor the currents on the sea surface. So we must not expose the drifter's body to the wind effect. So if we want to reach the maximum irradiation, we should expose the drifter into the sun. So that's the first thing that we can find problems here. Also, we highly depend on the deployment latitudes, because if we're in the upper north or in wherever on the Earth ocean, we might find a really low solar irradiation, and obviously also really some months that we don't have sun. Also, we can find something like this in the picture. As you can see, the biofouling, because seas are really hostile environment, so we can find some drifters after some months of deployment that are covered from biofouling. So solar is not the final solution. That is why we started to think on a wave kinetic energy harvester, or maybe with some hybrid solutions that we can add to a drifter to scavenge energy from different sources. My main topic is the wave kinetic energy harvester, which is the topic of my PhD, which I'm currently doing now. So the first step is to design a kinetic energy harvester, is to study the motion of the drifter. We have used OrcaFlex simulator that you can see at the left part here. We have modeled different shapes and kinds of drifters and different environmental seas with high waves, slow wave, to see how is the movement of a real drifter. And we have also deployed different drifters with several accelerometers embedded inside to compare the simulated results with the current experimental ones, to see which is the movement of the drifters, to see which is the energy that we should scavenge. What we saw is that we have two main movements. The first one is the vertical vibration of the drifter, and the other one is the pitch and roll motion of the drifter. If we saw the power spectrum of the vertical vibration, we see that the energy is placed at a very low frequency, most of all the frequency of the waves movement. But also we have some harmonics of that movement. And also we have the natural frequency of the buoy, which depends on the shape of the buoy, the radius, the mass, the placement of the center of gravity, which can be aligned to one of these harmonics and can be incremented. So as you see, the movement is nearly around between 0 and, let's say, 2 Earths, where the movement and the energy of that movement is. So in this picture, you see a little bit of explanation of the power spectrum available, where the energy should be. And the best performance of a linear shake is centered at one of these frequencies. So the big challenge here is how to take the whole spectrum of that energy. We have been working in the past with different several designs here at Universitat Politècnica. We started with some electromagnetic solutions. We have a toroid with different windings around, and we have a magnet ball rolling inside, moved by the movement of the waves. As the ball is a magnet, it induced some current in the windings. Then we moved to piezoelectric solutions. So we have a piezoelectric that inside different piezoelectric boards on a cylinder that vibrate thanks to the different spikes that make them vibrate. But we find many problems because we highly depend on high frequencies, and here we talk on really low frequencies. So that's why we move on our late design, which is our actual design, what we are working now, which is an inertial pendulum type harvester. It is based on a proof mass attached to a pendulum arm, and the main body is attached to the body of the drifter, so it moves relatively from the motion of the drifter, from the vertical vibration and the pitch and roll motion. Then we have a gear system that transmits the rotation to a flywheel, where the rotation is accumulated, and that flywheel drives an electrical DC generator. Is a really small one. I don't know if you are seeing my screen, but we are talking of device small like this. So we have a really big limitation in space and drifter. So we are talking of really small devices like this that are driven thanks to the movement of the body. So this is the actual device that we are talking about. And here I put an animation of that device placed on a linear shaker. Here there is not the DC motor, but you can imagine that will be placed here. And how it converts the linear movement into rotation, and then the micro generator will convert it into electricity. So having this, the output that we will find will be something like this, which is the voltage in the output of the generator, which will have AC and DC components, as you see, because the flywheel rotates, but also accelerates and decelerates due to the movement of the pendulum. So, as I presented the device, now we should talk about the power management here, because it is a aleatory and anarchic energy that we are providing, but we should have a power management unit which takes care of several parts. First is the energy extraction. We want to maximize this energy extraction, so we should have a maximum power point tracking technique to achieve this maximum extraction. Then we need a storage control to monitor the energy from the energy storage element to the load, and also from the energy harvester device. And then to provide a regulated output to the load, which will be the electronics of the harvester. So let's talk on the power management part. As I explained, we are working on a DC motor, which can be modeled with the Thevenin model equivalent. It will be AC source and an internal resistor. We have characterized these different DC generators. As you can imagine, as for the Thevenin model, the maximum power point is found at the half of the open circuit voltage. That will happen when the resistor from the load equals to the internal resistor of the generator. There are many methods to perform the maximum power point tracking technique, as perturb and observe, which is complex and power consuming, constant voltage providing, which is simple but requires manual tuning. But on the different commercial power management units, we commonly found the fractional open circuit voltage, which periodically samples the open circuit voltage by opening the electrical generator and then places the half of this voltage to acquire the maximum power point. We have worked with several commercial power management units. I won't get into details, let's just put it here. We have worked with Analog Device, with Texas Instrument, and also with this EP's company. They pretty much work similar, but I want to just highlight this parameter, which is the sampling time, which is very important for us because we are talking on movement of the drifter between 0.5 or 2 Hz. So these other ones are more thought for solar solutions because the changes are really slow. So APs are bringing us really good performance. We're just starting to work with this board. So we have talked about the energy harvesting device, the power management unit, and also the energy storage element that can be a rechargeable battery or supercapacitor, and the load, which will be the electronics of the drifter. But we have two main challenges here. The first one is how to monitor real time the energy that we are generating with the kinetic energy harvester and the power management unit efficiency. We have a test on the sea. And how do we emulate a different sea state and different sea dynamics in a controlled environment? To start with the first question, we have developed and designed a real-time power monitoring drifter, which has embedded the kinetic energy harvester that you can see here in the middle. Also, the power management different boards that we have used and an energy storage element. And here inside, we monitor the power input and power output on the power management unit, thanks to a microcontroller, which is an Arduino based. We also have information about the movement of the buoy thanks to an inertial measurement unit, which provides acceleration and gyroscope data. And all that information we save with timestamps thanks to a real-time clock module. And also we save all the data to an SD card. But what we have also designed is to send this data in real time. As the drifter is into the water, we can send this wirelessly with Wi-Fi connection to a computer, which has a LabVIEW application to receive this package, so we can see in real time what is happening inside the drifter. And you can see here an image of the drifter with the different parts. So this is the first prototype design inside with the drifter and with electronics. And the first test that we already have done to test the performance of the kinetic energy harvester on the sea. As I already showed, we have tested here the whole system, the kinetic energy harvester device, but also the power management unit in a linear shaker, which is not the perfect environment, but it's the first one to test how it works in a movement, in a linear movement. Then we used the simulations from OrcaFlex, which provide us information about how the drifter moves into the water. So we have the acceleration of the drifters, and we use this data to move a robotic arm, where we can simulate a more real environment to see how it moves in the drifter in the water. Then we use a waveform, which is a linear channel. It's a 100 meters long channel that we can emulate different sea states. They are just regular sea states, but it's enough for us. And we can say, okay, I want 0.5 meters high and 5 seconds period of waves, and you can emulate the situation. And with our computer, we can go there, deploy our drifter, and see in real time what is happening inside. And finally, we are starting to deploy it in controlled areas. We are just in the preliminary test, but we are so excited to do more tests in the sea. To finish my presentation, I would like to show you a video that we have prepared. I'm not sure that you can hear the music, but anyway, it's not the important part. Here you see some images of the simulations that we did with OrcaFlex, where we can get information about accelerations. This is the simulation with using an X of the movement of the device, how we turn the oscillation into rotation. Then images of we already saw that image of the harvester in a linear shaker, how we turn this movement. Here, let me pause this. You see how is the user interface that we have deployed with information about the pitch, roll, yaw, and the accelerations, but also information in real time of the energy that we are generating and of the efficiency of the power management unit that we are using in that moment. Here you see some images of the first test that we did on the limb waveform with several drifters. Then here you see a simulation of the KUKA robotic arm. That was when we were preparing the simulations to be performed in the KUKA facilities. And here are the real images of the test. And finally, some images of the first prototypes that we have already deployed on the sea for just short time, but we're preparing a long deployment. And these are some aerial images that are nice. So, thank you to Meloa project and to the SARTI and ICAT groups, which are the groups I work for, and the grant I have from Universitat de Catalunya. And thank you for listening. I'm open to answer any question, and also if anybody wants further information, I will be happy to share my work. Thank you.
Thank you very much, Matias. I think we already have a couple questions in the chat box.
Okay. Let's see. Yeah, really small. How small? The balls are between 10 and 20 centimeters of the diameter. I mean the drifters. And the prototype of the kinetic energy harvester is like this. I think you can see it's 8 centimeters of diameter. Yes, we are. The smallest is this one, 8 centimeters, and we are scaling it to 12, but not much because drifters are small. Drifters are not bigger than that. We are also thinking on scaling into a big solution, but for the moment we're just working with drifters. So for the moment we just work with 8 centimeters of diameter. We have also another question from Panos Alevras. Where is the very rarely periodic landing to ensure the prevention that may have a great impact on the type of the pendulum motion? Yeah, it is. Do you take random into account in design and optimization? We are trying to change the design of the kinetic energy harvester, and we know that waves can change from one period to another really fast, and they are anarchic, so they are changing. What our device have is that it is a 3D pendulum type, so easily it can take energy from all the directions and the different periods, and as it accumulates the rotation in the flywheel, we can achieve to get that energy using a DC converter, a DC generator. From Letty, thank you. Oh, interesting talk. What it would be possible to know what is the piezoelectric energy harvesting material you're using in your device, please? I cannot answer this specific question, but if you send me an email, I will be open to share you the different publications that we have for this kinetic energy harvester solution, and I can send you the data. We have more questions. Due to coverage over the ocean, do you will need satellite communication? Yes. Now we are using Sigfox, which is a LP1 low power wide area network communication, because for the moment we're just working in coastal areas to do the tests. But in the future, we are thinking on deployment into the sea. So we are thinking on satellite communication. We want to work with Argos solution, which is the solution that Meloa project has been implementing. People from CLS from France are working with us, which is a partner from Meloa consortium. So yeah, we will use Argos for the moment. Can you please say your email after the presentation? Yes, for sure. I will put my email here. So I think that's all. Thank you very much for all that questions. I will put my email here.
Thank you very much. It was really a very interesting presentation, and thanks to everyone who has participated today. It's really amazing to have a successful first day and with minimum amount of technical glitch. And I'll just share the. Yeah, thank you, Matias, once again. All right. So this brings to the end of first day of our 3 days energy harvesting dissemination event, 2020. And tomorrow we have 4 other exciting presentations waiting for us. So I look forward to seeing all of you for tomorrow's session. And thank you once again. And it will really help a lot if you can fill in the feedback survey either now, today, or maybe on Friday. Oh, we have a question.
Yeah, can you hear me?
Yes.
Well, I wrote my question, but I'm sure you can see it. Tomorrow I can assist. I don't know if you will record the sessions and will be available afterwards.
Yeah, it will be recorded. I'm not entirely sure what platform will share it afterwards, but the sessions are recorded.
Okay, thanks.
All right, thank you. All right. Yeah, once again, thank you very much, and please join me in thanking the presenters, and I'll see all of you tomorrow. Thank you very much. Thank you, all of you.
Thank you. Bye.
Thank you.